Hello and welcome to this video about the basics of random numbers in Python. Today I'm first I'll sort of motivate why we need randomness in our economic models, so why it's useful, and then I'll show you how to actually draw random numbers. There's sort of a couple of different ways to do it, but the way I'm going to show you built on NumPy. It has a submodule called random. And then there's also scientific Python has a stats module which works in a kind of different way. It's actually also built on NumPy, but sort of have a few different functionalities. And then I'll show you some of the distributions you can draw and how to visualize them. And I'll also talk about how to load and save variables in Python, which can be useful when you're doing random numbers, because sometimes you draw a lot of numbers and you calculate a lot of results, will take a lot of time, and then you want to save it so you can watch it later without having to rerun everything. And then I also have an example where you create a Python class to generate random numbers. So let's just dig into it. I sort of said this already. Here are some links if you're interested in the documentation, and there's a data camp on Pickle, which is what you use to save your variables and load them. In terms of import from the notebooks, it's sort of common. We haven't been doing it in a lot of the other videos because we sort of want to show which modules we're using as we're using them. But the normal thing to do when you're writing code is to import all the modules that you want to use at the beginning of your notebook or at the beginning of your code. So you sort of show, okay, this is the modules that my script depends on, and then sort of have the code later. So we'll begin to do that from now on. So we'll import Pickle because we need it later. We'll import NumPy. From SciPy stats, we'll import norm, which is the normal distribution, and then we'll import all this stuff for plotting. And setting some default values for how we want our plots to look. This one. Yes. Okay. First, we'll motivate. Why do we want randomness? We have economic models, and we want to be precise. Well, what's the deal with this randomness? Imagine an exchange economy. So economy where people have goods and they trade with each other with these goods, sort of maximize their utility. So in this economy there are two goods and there are n consumers, so there are many people in this economy. They have Douglas utility function, and they have heterogeneous coefficients which are uniformly distributed. So everybody have the same utility function, but they all have different alphas indexed by this j. So they sort of weigh good 1 and good 2 differently. It's uniformly distributed, so sort of flatly distributed between two numbers, which we'll decide later, but they are between 0 and 1, as we normally define alpha to be. And there's sort of their endowment, so how much they initially have of the two goods that they can trade with are equal across people. So everybody have 1 of good 2 and then k of good 1. And we'll define k later, but it just has to be above 0. And here we say good 2 is numeric, so sort of what matters is not how many have of good 1 and how many ever have of good 2, it's how much you have of good 1 relative to good 2. So we can just set one of them to 1 and then let the other vary. For each individual in this economy, so for each j, then we know the solutions because it's Douglas, so we just use the analytical solution just to make it a bit easier. And then we know that, okay, good 1, then they'll use alpha j share of the income on good 1, and they'll use 1 minus alpha j share of the income on good 2. And that income is sort of implicitly defined by their endowment, and they have K good 1 goods, and they get price 1 for that, and they have 1 good 2, and they get price 2 for that. So this is their income, and we just plot that in here. So this is the implied demand function for each person, and so given that you have a large N, or capital N, number of persons, so you have a vector of alphas, and a given set of prices, so we'll assume we have solved that, then you can sort of calculate the equilibrium by summing the demand for each person over all the persons. So this is the demand, and the supply will be given by their endowments, which so you just sum over how much they got of good 1. So this is their demand function for good 1. Then you sum over how much they were endowed with for good 1, and that's just capital N times K, because they all have the same. And for good 2 you have the same, you sort of sum over the demand, and their supply will just be capital N, because we assume that everybody has 1 of good 2. Our problem is now that we want to solve for the equilibrium prices. So what prices satisfies this condition? And to do this, we require a distribution of agents, because we have this large economy, which a lot of agents would have heterogeneous coefficients, and to sort of simulate that, then we need to draw these agents out, so we can sort of calculate on real numbers, and we want to draw random numbers based on some distribution, because then it's sort of fixed. So we sort of assume a behavior, so we assume that these alphas come from some distribution, but we can't sort of create the distribution without having any randomness. There are some ways to do that, but like the normal Monte Carlo way would be to sort of actually just draw random numbers to emulate the distribution, and then calculate on them. And then if you have a large enough N, then it will sort of behave as the economy that you assumed, and this distribution that you assumed. So we want to create this distribution of agents from randomness, and to do this we need a random number generator, or an RNG. Okay, so how do we get random numbers on a computer? This is actually, I mean, when I first thought about it, then I thought there'll probably just be some random function. And yes, there is like a random function that gives you random numbers. But the way a computer does this is sort of weird, because like in a computer, everything is ones and zeros, so there is no true random on a computer. There is true random in physical observations, so radioactive decay and some background noise, and roulette wheels, or just throwing a dice, and then algorithms. So the computer can sort of emulate that with something called pseudo-random numbers. And they aren't really true random, so what the computer does is that it sort of does some calculations, does some operations, creates a huge number, then it maybe takes middle digits out and does new calculations, sort of. It does a bunch of stuff, which means you can't predict what the number will be, and it will be as good as random, even though it's not true random, because you're doing operations, and if you have the initial number and you know what the operations are, then you can actually predict it. But you shouldn't be able to predict it without knowing these two things. And also each new random number shouldn't be correlated with the former random number, unless of course you're putting a distribution what they actually are. If you want to know more about how this works, then there's like a video on it, but it's not like something we'll ask you for in the exam. We'll just assume that these random functions actually work. So you can, as I said, you can use the NumPy module random, and here I just say I want a random integer that's called randed, and I want it to be a random integer between 0 and 10,000, and then I create a size 5, so I want 5 random numbers, and then I just print it, and then I get 5 random numbers, which sort of equal probability for each of them between these two numbers. And if I run it again, then you can see that I get 5 new random numbers, and this will happen each time. And this is good. We know they're random. So I got a low one this time. But it's also, when you're doing scientific programming, then you want to be able to reproduce your results. And sometimes you want to make sure that when you are making some changes in your program, then when you see changes in your results, then it's actually due to changes in your program and not due to changes in the new random numbers you're drawing. It's typically not a problem because you don't want the random numbers you're drawing to have an effect, because then you're probably drawing too few random numbers. But it's nice to know sort of how things work exactly. So in order to get the same random numbers, once you sort of close down the program and open it again and rerun stuff, then you need to use something called a seed, which fixes the algorithm and the initial numbers you use to create random numbers. So if you choose a seed, you can do this by writing np.random, and then you choose some number. That can be any number. Then you choose a seed, and then you can sort of draw random numbers which are random given this seed. But if you set the seed back to that number, then you will get the same random numbers. So you can see here I get the same numbers. If I write a new seed here, then I get different numbers. This uniform just draws from the uniform distribution, so a float between 0 and 1 with sort of equal probability at each point. So setting a seed makes sure you get the same random numbers each time, and it's sort of a good form generally when working with random numbers to set a seed at the beginning of the program and then have that be the seed for the program. Because you can also, if you just don't have anything here, then you set a seed for the first random numbers, but then the program sort of moves on. So when you call the function again, you print new random numbers that are uncorrelated with the first random numbers that you printed. But sort of they will always be, so the second time you call this function, it will be the same numbers. That was the point. It's important. So that's how seed works. And you can also sort of get the state at a given point in time and set that state. If you're doing some process where in the middle of it you want to make sure that you're drawing the same random numbers each time. So you get the state where you're at by writing np.random get state. And then you draw some random numbers. And you can actually see it's funny, these numbers are the same that we got if we did not set the seed up here. So this vector is the same as here if we didn't reset the seed. So that shows that they're random numbers, but they're sort of fixed if you know the seed. So we're drawing this random numbers, and then if you draw again, you're changing the state, and you get new or you change the state when you draw random numbers, and then when you draw new random numbers, then you get new random numbers. But you can sort of go back to your initial random numbers by setting the state to whatever it was before you drew these numbers, and then you get the first numbers up here. Yeah, and it's important also, common practice, just to set the seed once per program. And you shouldn't like change the seed, because Python will automatically change the seed as each time you draw. And sometimes this state stuff can sort of be important if you're doing different calculations, but you want these numbers to be the same. So if you're trying to estimate something with different estimators, and you want that to be based on the same random numbers or something, then you can use this get state, set state stuff. But you shouldn't reset the seed inside the program. So now I'll show you a few of the different, like there are a bunch of distributions. If you search numpy.random, whatever distribution, student t distributions, something, blah 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 distribution, Poisson, you can get them all. Not all, but more than I know, at least, more than you learn at the economics program. So here we're showing you the normal distribution. Log is sort of the mean. Scale works as the, I can never remember if it's the standard deviation or the variance. Maybe it'll say standard deviation, of the distribution. And then size here is sort of how many numbers you want to draw. So here we're drawing 10 million or 1 million. 1 million. And the beta distribution also has some parameters, which I can't remember right now. It has an alpha parameter and a beta parameter. And then we have the uniform distribution, which is sort of this flat distribution. And then you can sort of set it, instead of the default is that it goes from 0 to 1. But you can sort of set different bounds. So here we say, okay, it has to be between -2 and 2. You can also have like a user-defined probability distribution, which is just basically that you choose a discrete set of numbers, and you choose, for each number, you choose the probability of getting that number from the distribution. So here we just create a vector of the discrete choices that you can get, and then you define the probabilities. Here we define it like this, where it's from a lin space, and then we take it to the power of e, or the exponential, and then we just make sure the probabilities sum to 1, and then we also draw a million observation from that distribution, and then we can plot it in histograms using so this sort of just part of normal plotting. And then to plot a histogram, then you just write hist.x, and then you can sort of, there are a bunch of different options. Alpha is sort of transparency measure, which sort of allows us to see what's going on for overlaying distributions. And you can see that sort of looks like you would expect. You would have the normal distributions here, which sort of looks pretty flat because we zoomed a bit out. The beta distribution looks like this, and the uniform distribution is totally flat distribution. And then you can see that our custom distribution just has these numbers that we've given it, so it can sort of only have discrete possible outcomes. And we can see that the probability is sort of rising, which makes sense with how we defined it as a lin space that is increasing. Then there's a task where I will not show you the answer, but I'll talk to you about how you can do it. You just follow this link, and then you can see a bunch of different distributions, and then the task is to sort of add it to this figure above. So find the distribution, draw random numbers from it, and then basically just add a line here where you add it to the plot. Yeah, so pause the video now and try to do it. Yeah, I hope you succeeded with it. Yeah, if this is a sort of a custom task, so it'll be hard for me to show you a direct solution, but if you're having a problem with it, then you should definitely ask your TA to explain to you how this works. Analytical results. Sometimes we want to compare distribution of numbers to a known distribution. So this is sort of, if we draw a normal distribution, then we know how it should look like. And in this case, you can sort of use the scipy.stats module, which sort of, it can draw random numbers, but it can also show you stuff like the probability density function or the cumulative density function and stuff like that, which is sort of, you know how the shape should look like, and you can plot the shape. So let me show you. In this instance, I should show you how the normal distribution works. So we want to create a distribution. I call it guess because we sort of want to emulate the random numbers that we have drawn. So you create you define a log, so the mean and the standard deviation, and then in order to create it in SciPy, then you sort of write norm, then you create an object which can create these random numbers and create the PDFs. So you create a norm, and then you input the log and the scale, the mean and the standard deviation, and then you draw random numbers using RVS, and then how many random numbers you want to draw. You can just, PDF is just a method from this object you have created, and so is the CDF. So you see here it prints out that the PDF at 0 is 0.5, and the CDF is 0.36. And then we can sort of plot this function. We choose a low and a high because technically the distribution, sort of the plot can go, because it's a normal distribution, then there's a very low probability that you can get minus infinity. So we want to sort of cut it off at where most of the mass of the distribution lies, which is between these two numbers defined by the PBF. And then we just create a lint space between these 2 points, and then we just plot the probability density function over these points by creating this vector on the different x's we want to look at. So these are the random numbers. So this is just the x from NumPy, and then we sort of draw this above it. And then we can see, okay, it doesn't really fit. And there's actually a task to make the histogram fit more closely. And yeah, if you know how to solve this, then pause the video. If you don't know how to solve it, I think the issue here is sort of that our distribution has mean 0.25 and standard deviation 0.75, while the distribution we drew random numbers from had, let me check, 0 and a standard deviation of 1. So this is more just to see that when we actually when we sort of have the same mean and standard deviation, then we get the exact same distribution as the random numbers. You can sort of see that it's not exactly smooth, the histogram, but it's very close. Yes. And yeah, as I talked about before, SciPy is all built on NumPy. So setting a seed will also affect the random numbers that you draw from the SciPy functions and objects you create, which is nice to know. So you can sort of still use numpy.random seed to fix a seed at the start of your program. Yeah, how to load and save variables. So as I said, the reason we might want to load and save variables is because we sometimes create many random numbers and do many different calculations on them. A good module for doing this is Pickle, which can save a lot of different kinds of data, so you don't really have to worry about it. So here I create some variables, a dictionary, a NumPy array, a tuple, and then I put them all inside a dictionary, and then I can sort of open, use this with open, some name, and then pickles have this .p name, and then I say I want to write binary as f, so I call it f, and then I just use pickle.dump my dictionary inside f. So I mean, it's already created, but when I run it here, then you see, okay, I can't open it here, so I can't really look at it because it's binary, as I said here. I wouldn't be able to read it anyway because I'm not a computer, but I can load it again in Python. So if I delete these variables from inside my notebook, then you can see, okay, I no longer have access to my dict, for example. I mean, I know it's here, but just play along with me. I no longer have access to it. What was inside my old dictionary? Then you can sort of just open it with this. Again, using Pickle, so you with open, and then you have the same file name, and then you say I want to read binary, and then you use pickle.load, and then you just set it equal to your data. So this is before it was my data, and then you dumped it, and then you want to say with open data pickle.load. I want to call it data now, and then you can unpack it, and then you have my vector, my tuple, my dict back inside your memory. Pickle is good all around. If you only want to load and save NumPy arrays, then you can use a function inside of NumPy, which is typically faster than Pickle because it's directed towards NumPy arrays only. So it's sort of, again, more restrictive in what you can do, but typically faster. Yeah, so now we create a dictionary of NumPy arrays. So we only have NumPy arrays, and then you can just use this saves function. And then the file type name is npset, and you don't have to do this all with open stuff. You can just unpack that dictionary like this and save it. So what you're doing when you're unpacking is basically you're creating keywords arguments implicitly from the dictionary. So this would be the same as sort of writing the keyword arguments out manually like this. So this star is just a nicer way of doing it. Looks a bit more concise. Again, we try to delete the data so we don't have it inside the notebook, and then we want to load it out. Now you have to do this with stuff. So you say with np.load the npset file you have saved, then you give it some name, and then you can loop through the files inside of it, which are each keyword argument, so this A, B, C, and now we just create a new dictionary with the whatever was inside of it. Yeah, and you can also just load it directly. I think even if you just do np.load of it, then you get a dictionary out. Not dictionary, but you can sort of take out the array, so it works as a dictionary. So we had A and B, not V, B and C, which were what we created up here initially. Yeah. Cool. I think that was everything about saving and loading numbers. Now I just want to show you quickly a class that can generate random numbers. And the example here is a class that's a dice, basically, and not one dice, it's a cup of dices. So you initialize it by saying how many dices there are in this cup. And then it has a method called roll, which just prints, it draws random numbers for how many dices you have, and you can have 1, 2, 3, 4, 5, or 6 as the outcome. It's a 6-sided dice, and then it prints the outcomes for the dices. And then this shuffle is sort of a new way to just draw new random numbers. Yeah, okay, so you shuffle the order, sorry. You shuffle the order. So you have the same random numbers, you just shuffling them around so they get a new order. Yeah, so this is how you sort of pack all of this into a single class, or some of this. Yeah, and then there's a small task, which is to add a method called roll and sum, which basically just is another row. So you draw new random numbers, and then you have to print the sum of the dice. So the sum of the new random numbers you have drawn. Yeah, and then the pass function here is so we have predefined the function for you, but because Python does not want you to have a function and then write nothing, then you have to write pass. So just delete this and write your answer. So yeah, have a go with it. See if you get something good out. Pause the video now. Cool. So the answer is basically just to sort of copy this code or call roll, then you will implicitly print whatever has been rolled. You could also sort of just have a new dice roll like this, then you don't print it, and then you print the sum of the dice. And this is what happens when you call roll and sum. Yeah. So in this lecture we have talked about NumPy random, how to draw random numbers, and why they are only pseudo-random numbers and not true randomness. And we will talk about SkyPy stats to sort of show the analytical features of random distributions, and then we talked about pickle and safes. And yeah, I've tried with examples to show you how important it is to have random numbers when you have heterogeneity, or to simulate heterogeneity, and I hope that came across. Thank you for watching.